Okay, everyone. So let's look at this week here, and you have an R assignment due Friday, tomorrow, and then a few pre-lectures due on Sunday. And this is the end of the pre-lectures. So from here on in, we haven't made any. I might make some new ones, but basically there aren't going to be many from here on in, pre-lectures. Okay, so what we're doing today is on confidence intervals and significance tests for the slope, and the homework for that I'll post right after class, and it will be homework 12 due Tuesday. So let's go to the document camera here and get started. So last time, what did we do? Last time we looked at confidence intervals for using the normal curve for the slope. Remember, we're doing inference for regression with just one x predicting one y, so we have a regression line, and what we're looking at is we know that every time we take a sample, we're going to get some chance error in our slope, some sampling error. So we figured out how to compute the standard error for the slope, and we used that to build confidence intervals. We said if we had a big enough sample size, then the central limit theorem kicks in, and the distribution of the sample slopes is normal. Now, what if we don't have a big enough sample size, okay? If we don't have a big enough sample size, then we're going to be using the t distribution, and it's going to be very similar to what we did when we used the t distribution for means, but now we're going to be using it for slopes. Okay, so this is where, remember we had the 4 assumptions to be able to do inference for regression, and the first one was, well, we're going to get a regression line, so our scatter plot should look linear. That was linearity. And then the other three assumptions previously were had to do with what? Had to do with the 3 assumptions right here. Had to do with the independence. That was our second assumption, that the errors had to be independent. They can't be linked to each other, like modeled as independent draws randomly, and equal variability across we didn't want something that looked fan-shaped like this, or where the variance changes across X. We want the same variability all the way across X. So those 2 assumptions allowed us to compute this standard error of the slope. But normality, we don't need normality to do this, to compute this standard error, and we don't need normality if we're going to be using the central limit theorem and have a big enough sample size. Where does this last assumption come in? This last 4th assumption, right here on page 119, comes in, the assumption of normality, comes in when we have a small sample size with an unknown, this is our usual 3 assumptions. Normality is one of them, if we want to use the t distribution. So we use the t curve when we have an unknown standard deviation of the errors around the regression line, which is almost always the case. When we have a small sample size, in this class we're just drawing this arbitrary cutoff of less than or equal to 25, because for the purposes of this class, we don't really need more accuracy than that. You can still use t with larger n, but it's just not necessary in most even though software programs do it anyway. So these are 3, and normality, normally distributed errors around the regression line. So when you have a small sample, when these 3 conditions are met, these are our usual 3 conditions are met, you can use t, and that normality is assumption number 4, right there. So I guarantee if you're in a higher level statistics class, you're always, when you look at assumptions for regression, you're always going to be talking about normality, in identically independent distributed errors, normal with 0, average, and sigma squared variance. That's what we're talking about now in less formal language. Okay, so now everything's going to be very similar. So you're going to think, oh, we're just doing the same thing over and over again. The only difference is this degrees of freedom here. Okay, so remember, when we did the standard error, when we were doing, in the past, when we were estimating a mean and we wanted to look at the sampling error around the mean, we said, okay, we use n minus 1. We have n minus 1 degrees of freedom here because we said, think about it, if you just have 1 point, n is equal to 1, you can estimate the mean, but you can't reasonably estimate any spread around the mean with just 1 point. You have no idea. But as soon as you have 2 points, you can sort of get an estimate of how spread out those 2 points are and how spread out. You can estimate a mean from that and then a variance. So you need at least 2 points. The first one, n minus 1 degrees of freedom. So you need at least 2 points. Now we have n minus 2 degrees of freedom because we're trying to estimate the degrees of freedom refer to the variability around our model, which is a line. So you can't, first of all, you need 2 points to even get a slope, right? But then you need a third point in order to estimate any sampling error, any around that slope. If you just have 2 points, you're going to get a single slope. You're not going to get, it'll be a perfect line. You'll have no error around that. So that's what I say here. You can't compute a slope with only 1 point, right? You need 2 points to determine a line. And you need a sample size of 3 to sensibly estimate the range of estimates that you'll get when you sample over and over and over again. Remember what the standard errors refer to. Those are our sampling errors. These refer to the variation. Each time we take a sample, a new sample, we're going to get some variation. And so we need a way to estimate that. Now we have n minus 2 degrees of freedom. Okay? Any questions on that? When we add another x, we're going to have an equation where we have 2 x's. We'll have a regression plane. And then we're going to have 3 points to determine a plane, so it will be n minus 3 degrees of freedom, and so forth. So these degrees of freedom refer to your variability around the model. All right. So that's what it's going to be. Now, you probably don't even, do you remember this from last time? From last time, just so you remember that the standard error without the plus of the slope, how did we even think of this? We thought standard error, it's a sampling error, but it depends on the standard deviation, standard error, standard deviation, the spread around the regression line. That's what this is. And then we thought, okay, we have our usual square root law divided by the square root of n. So that's what it looked like. But then remember we said, okay, but to get the right units, rise over run, right here, we'd have to divide by the standard deviation of x. Otherwise, we just have y, not y over x. All right? So, and then this is what it looks like when so the only difference is what? We can just write it. Remember, standard deviation of the errors is the square root of 1 minus r squared times your standard deviation of the y's. And then so that's what we have in the numerator, just the same numerator. And the only difference is in the denominator, we're subtracting 2 instead of the 1 we had before. That's the only difference here. That's because of this plus. We're making it bigger in the same way we did when we were doing the mean. All right. That's the idea. So we have n minus 2 degrees of freedom. And now, if you really wanted to, there's nothing wrong with using, this is a better estimate if you have an unknown standard deviation and you have a large sample. You can use that too. You can use that, but most people don't. Because because basically you can do it, but people don't. Because by the time you really need to do it, you're using the t anyway. Otherwise, it really won't make much difference. This is exactly the same. I sound like a broken record to myself, but it's probably good to hear it again. This is exactly the same thing I said before with the t-distribution. Doesn't it sound completely familiar to everybody? Doesn't it? The only difference is this 2 instead of the 1. That's the only difference we're talking about. All right, so again, so now we're going to do our 2 differences between using the normal and using the t. The first one is, okay, this one. So we're just going to make this standard error a little bigger. That's the first one. And we just didn't bother to do it for the z. If you do it, it's not wrong. Then, now we're going to, this is the big one, that we're going to use these t-curves instead of the normal curves. And the t-curves are fatter in the tails, and I should add, and flatter where in the middle, the same thing. Which means for a given confidence interval, they're wider, right? So the t star, the critical value, is greater than z star. That's why the confidence intervals are wider because, well, here, let's just look at it. All right, so now here are the t-curves, and k, I copied this from a book or chart where k was the degrees of freedom, which is n minus 2 for our slope. So k equals 1 degrees of freedom means what? That our sample size, n, is equal to 3. Remember, that's the smallest sample size you can have when you're doing this. If you just have a sample of 2, you have a perfect line. You don't have any error around it. So n equals 3. All right? So now look at which one is n equals 3 here. That is the one that's flattest in the middle, the most extreme. First of all, the normal curve is the one that's highest in the middle and skinniest in the tails. So it's like a dotted or dashed line here. Let's just do it so you can really see the difference. Let's dot it here or dash it. See, it's skinniest in the tails and tallest in the middle. That's the normal curve. And as you can see, as your degrees of freedom, your sample size gets larger, it gets closer and closer to the normal curve. This is exactly what we did before. So this is 1 degree of freedom right here. K equals sample size of 3 for a line. And let's do that so you can see the difference. You can see it's flatter in the middle and fatter in the tails. And of course, they both have to have 100% area. So it's the same area, but for confidence intervals, it's shorter in the middle, the t, so you have to go out further for the same thing. So for example, if you wanted to do like, let's do a between 1 and negative 1, you know on the normal curve, if we go up here, on the normal curve between 1 and negative 1, right here, I can just, between negative 1 and 1, and that would be going all the way up here. We can make the normal curve this area is, you know, what? 68%. So that's 68%, going all the way up on the normal curve. But on our, it looks like it needs to focus a little better. Okay, but on the t-curve with 1 degree of freedom, we would have to go out further. We actually, to get 68% of the area, we have to go out to about 1.8. So this is the most extreme difference. So if we go out on the normal curve, on the t-curve, so this would be between, on the t-curve, t is equal to negative 1.84 to t equal to 1.84. That would be t star for what? For 68%. So this would be, let's get a different color in here. This area, it's shorter there, but it's fatter on the edges. So this area right here is also 68%. But you have to have a wider interval. This is exactly what we already know, but I'm just illustrating it again. Whereas here, the Z star for 68%, our critical values, would be between -1 and 1. So that's what I mean. If you were going to do a 68% confidence interval with a sample size of 3, this would be the difference with a sample size of 3, you'd have much wider interval using the t. Okay? Any questions on that? Does that make sense to everybody? All right. So now let's do an example. And I was just looking at our own data on this because I asked you this on the last survey, GPA versus drinks. Most people would think that, you know, the more you drink, the lower your GPA. I mean, I'm sure you're told that all the time, that drinking's bad for you, drinking alcohol excessively. And it is. But how bad is it for your GPA? So I figured I'm curious about this question. So we got a correlation, I was just looking, of about -0.2. I can show it to you if you want. Do you want to look at our data? Anybody want to look at it before we start? Raise your hand. Okay, might as well. So we haven't been doing much of the fun stuff, right? So let's go to the PC. And, all right, here's our scatter plot. And this is from our statistics here. From this class, 320 students this semester answered. So their average GPA was about 3.5. That's very high. And the drinks per week is pretty moderate, 3.5 average drinks per week. Okay? Now, the maximum was 45. Oh, that's because I deleted some people here. There was higher. Let me refresh this because I can show you the real data, so I have to start over. See, I deleted these points up here because there's big outliers, but I think they're real data. So let's go back to it and let's look at it. Now we can look at the statistics. And yeah, the maximum is 50. So as you can see, this student right here drinks 50. I don't know who it is. It's just observation 105 and observation 136. Drink a lot, but look how high. This one has a 4.0. And so I looked to see the rest of the data, and it looks real. I mean, we can't throw it out. I don't think it's a typo. I mean, if you look at our height and weight, there are typos. There are people who say they're 8 feet tall and only weigh 100 pounds. That's impossible, right? But this, I don't think it's impossible. I looked, everything else looked realistic on it. One's a boy and one's a girl. So, but I don't know anything much about them. You know, I can't tell who they are. So that's the idea. So now, just by we have an R equal to 0, negative, it's slightly negative, 0.15. So I wanted to see what happened, how much of an influence they had if I deleted these. Because I usually get about -0.2. So let's see. So now we're going to delete them. And can you see when I delete these points how we're going to get a stronger correlation? Does that make sense to you? Watch this number. It should go up in absolute value because we're at the end. Remember, points way at the extremes are going to affect the slope more. So I'm going to delete this person, see how it went up, and delete this person. And then we get about what we usually do, -0.2. All right, now this person doesn't drink at all, but has other problems, right? I mean, this is not doing well. If we delete this person, who's got a very, very low GPA, what do you think is going to happen here? I think it's going to go up. Let's see. Yep, it goes up a little bit. So you can find yourself on here. There are a lot of people bunched here. And so some of the points represent more than just one person. Now, what does this look like? Can we even analyze it? We should show the errors. So let's look at our errors. And they look okay. I mean, it's not really a we just don't have much data out here. But where we have data, it looks pretty good. So it looks like we could do regression on it. Okay, so that's the idea. And so imagine that we chose 20. Okay, so now what are we going to do? That's our whole, you can look at this stuff, it's really interesting. All this stuff, I've been looking at it, who you're supporting for in the primary, all sorts of stuff on here that you can look at, that's fun. So you know how you can access that, right? You just go to, well, you know, the data program. Let's go back now, and any questions on that? All right, so here we are back at our document camera, and let's pretend that we did a similar survey, but I randomly selected 25. I want to do a t-test. That's why we all have a small sample. Let's say we selected it from all the thousands of U of I students, okay? So, now, do I need to know exactly how many U of I undergrads there are? No, because this is the only number that's going to be figuring into our calculations. All right, we want to set up a probability model. Now, the probability model always has the entire population. So we want this null model is going to be what? It's going to have this scatter plot. It's not really a null model yet, is it? Because we don't have a null hypothesis. This is just our population scatter plot that we're randomly selecting from, right? We don't have any null hypothesis. That's going to be the next section. All we're doing here is confidence intervals. So we have a population scatter plot. Okay? And we don't know what's in here, but there's thousands of points. This is, we're predicting GPA from drinks. Okay? So this is X and this is Y. And we just have, we have some relationship in here, but we don't know it. We think it probably is slightly negative or heavily negative. Most people think it's very negative, but we really don't know what it is. So what we're trying to do is estimate what the regression line is in there, what the slope is. That's the point. So what we're doing is we randomly draw from here, randomly choose n equals 25 points, and it's without replacement. We're not going to throw the students back in. Now I should say here, so this is the n. Now what's our big N is our population size, but it's not going to enter into our calculation, so it really doesn't matter. So I'm just going to say thousands of points, one for each U of I student, maybe 30,000, however many undergrads there are. And then we get these sample statistics. So for example, there's what we got for R, and we got the average. This is based on Stat 100, and they drink a lot more than 200. So Stat 100 sample average is usually around 10, and their GPA is lower. So this is all based on Stat 100 stuff. So I should update it for you guys have different, typically have about 3 or 4 sample average and higher GPA. All right, now, do you remember how from this, we're just doing this is so far no different because we haven't, this is the same. We just want to calculate our sample slope. So we want to calculate our slope, our sample slope, which is the Roman. We have 1x, and this is the coefficient in front of it, not a Greek letter. So our sample slope is R times SDY over SDX, and you need to know that formula. Ingrain it in your brain. This is going to be on the exam and they're not going to be given to you. And it's easy to remember. Y over X, rise over run, and the correlation coefficient right here. Stronger the correlation, the bigger the slope will be here. given the same SDs. All right, so let's do it. And we get negative 0.2 over the ratio here. So 5 over 0.5 or 0.5 over 5, it's y over x. So it's 0.5 over 5. And please, on exams, I didn't realize that in the notebook I put x on top all the time and y down there. Y is always whatever you're trying to predict. So don't think that it's always going to look like this chart. Okay? So now we do this and we get negative 0.02. What are the units here? Drinks per GPA point. So what that's saying is on the average, for each extra drink, your people's GPA is lower by 0.02 of a point. Okay, not a big effect at all, but we want to know, is it real? I mean, is it negative in the whole population? You might want to think about that. But for now, we have to okay, so that's the slope. Now we're going to calculate the standard error plus for the slope. Okay? Now, all right, do you remember how we're going to think about this? Okay, if you forgot, it would be standard deviation of the errors over, now it's going to be not the square root of n, but the square root of n minus 2. That's the big difference. And then times standard deviation of x. But, so that's the n minus 2, because we're doing this plus. All right, and so this standard deviation of the errors is the square root of 1 minus r squared times the standard deviation of y over the square root of n minus 2 over the standard deviation of x. So that's what we've got here, and we can calculate it. So we'll take the square root of 1 minus negative 0.2 squared, that's our numerator, right, over the square root of 25 minus 2, and then times this ratio, 0.5 over 5. And I did that, and I got, it's always, standard deviation, standard error is always positive, these numbers are so similar, so I'm just going to go out to 4 decimals so you know you won't get these two mixed up. Okay, so that's our standard error plus. Okay, so now we can use the t-distribution to build confidence intervals. And let's do that. And we're going to get these critical values of t off. Remember, there's all the different t curves. So we have to first calculate the degrees of freedom, make sure, because that critical value is going to change with the degrees of freedom. And that's n minus 2. So that's what's right there? So that's 23. So we're going to be looking at the curve with 23 degrees of freedom. All right, so a 95% confidence interval is going to be what? Do you remember it's the usual thing? You just take your sample slope, which is right here. I'll just write sample slope plus or minus t star times the standard error plus for the slope. So that's all we're doing. Okay, so what is it? The sample slope is right here. Don't get it mixed up with the r. So that's negative 0.02 plus or minus, well, we know this part, the standard error, the slope. We just need to get t star. So we have to get that. All right, so what are we trying to get? Just to draw a picture of it. What we're trying to get is the 95% for t curve with how many degrees of freedom? 23. We want to get 95% in the middle. So we want to get those t stars that are the critical values here and here. What are they? They're going to be bigger than 2, or 1.96 for sure, bigger than 2 because that's what it is for z. So let's find out what it is. So we go to the back of the book and the t-curve. All right. Now, the way this t-curve is, it just gives you the right tails here. So this corresponds to the 95% because it's 2.5 in each tail. So we have to go down and look at degrees of freedom 23. Whoa, way down here, just look there. And the 95%, so we go 2.07. Remember, you expected something bigger than for the z, it is 2.07, but we have a lot of degrees of freedom here relatively, so it's getting close to the normal. All right. So that's our answer. So we'll put in, this is negative 2.07 and positive 0.207, and that is what our confidence interval is. Okay, now I don't have room right here. Where should I put it? I'm just going to put it right up here. Okay, so what is it? It's between the lower limit is negative 0.062 and the higher limit is 0.022. So that's our confidence interval. Okay. Now when you look at this, I want you to see something. Do you see how that includes 0? That includes 0. So that means that we can't be reasonably confident that there's absolutely no relationship in the population. A 95% confidence interval, including 0, is equivalent to not rejecting the null. Right? 0 is in our confidence interval. That means the null is that our slope's 0. So it's a similar thing, very similar. Why don't we do it? So this is the standard error. Okay. Why don't we? Should we look at this further? A 95% confidence interval, including 0, like ours, means we really can't reject the null. Does that make sense? We really can't. Because our estimate, we're 95% sure that the true slope is inside this estimate. And isn't 0 inside that estimate? Isn't it? So that's why. I mean, if you draw the picture, it doesn't really depend on t or z. It's the same idea. Let's just draw the picture here. Okay? Now we have 95% in the middle. That means on each tail, on each we have 2.5%. Now, if we include 0 in here, 0 is right in the middle, that means that our estimate is somewhere in here. So we can't reject the null. To reject the null for a two-sided test, wouldn't we have to be outside that range? We reject the null when we're outside that range for a two-tailed test. So this is what I'm saying here. 95% if your interval includes 0, that's the same as not rejecting the null, as not landing outside for a two-sided, right, at alpha. Or we should write that down, or for a one-sided would be beta is, in this case, would be less than 0. We think that it would be less than 0 at alpha equals 0.025, 2.5%. This is 5%. Or, of course, it could be the other way. But in this case, it makes more sense, we think, that our null would be that we'd get a negative slope. Okay? So those two things are equivalent. And I should write down that a 95% confidence interval not including 0, not including 0, is equivalent to what? If you land outside here, that's equivalent to rejecting the null. With all that being true. And we're going to look at this. I'm going to ask you this on your homework, and we'll do a significance test in the next chapter. And you can, I think it's very intuitive that they're equivalent to each other. Okay, so now let's compute the confidence interval. Any questions on this before we go on, just this idea? It will come up again and again and again. People will, instead of doing a significance test, if they do a confidence interval, they'll just see, does it include 0 or not? They'll look at that, and then they'll know if it includes 0, we can't reject the null. All right, now, so compute the confidence interval using the standard error of the slope and z. Now, first question, will the confidence using z be wider than using t? Would the confidence interval be wider using z or narrower? What's it wider with, t or z? It's wider with t, so with z it's going to be narrower, right? Okay, so what is the question? Will it be wider with z? No, it will be narrower. Z will be narrower because z star is going to be less, right? It's higher in the middle. All right. Now, the standard error of the slope. Okay, what's the relationship here? Which one do you think it is? We know, if you know the standard error plus, which one do you think it is? This one or this one? Think standard error plus, that little plus sign says it's bigger. You have more uncertainty, more sampling error, because you have with the t, when you're using standard error plus. So if we want to make it smaller, we're going to have to multiply by a number less than 1. So is this less than 1, or is this less than 1? This one's less than 1, and this is less than 1, smaller in the numerator. Okay, does that make sense? So you know how to switch back and forth. If you have 1, you'll know how to switch back and forth. And then in the 95% confidence interval using z. We're going to do the same thing, okay? Same thing. We start with our sample slope, plus or minus, but instead of, so it's going to be the same thing, sample slope, plus or minus, but instead of the t star, we're going to use the z star, and then we'll just use the regular standard error. That's what we'll do. And you'll see we'll get a narrower confidence interval. We'll see if we still include 0. Okay, so we have that, plus or minus. For 95%, you could use 1.96, but let's just do what we've been doing and use 2. So that's 2 instead of 2.07, and a slightly smaller standard error here, which is going to be, how are we going to get our let's use this right here. So we have, let's just do this. So we can get the regular standard error by saying what? We'll multiply 0.0204 by 23 over 25. And I did that, and I got this. So that will be our standard error. And then I still got a negative lower limit, but it's a little bit narrower than this one. Okay. That's not right, is it? I have to get bigger. Oh, no, that's right. Okay, so that's what I got. This is narrower. Okay. Any questions on this? So why don't we highlight this? right here. And star it. And this is the reasoning. Since the confidence interval includes 0, we can't be 95% confident that there's a negative correlation in the population. In other words, a small negative slope in our sample could easily be due to chance sampling. So that's the idea. And any questions? And here's our summary. So here, this might be useful because we're going to be talking about degrees of freedom a lot. This type of degree of freedom we're talking about here is variance around our model, and the degrees of freedom is equal to the sample size minus however many parameters in our model, meaning like with the mean, we're just estimating one parameter, the mean, and with a line, we have two parameters, the intercept and the slope. 2 points determine a line, whereas with the mean, you just need 1 point. So that's a way to think about it. We're gonna be talking about this a lot when we get into more parameters, that it's always gonna be n minus the number of parameters in your model. So far, we just have n minus 1 and n minus 2. All right, any questions on that? So let's go now, and what we're gonna do now is do a significance test for the slope, and we can do both a z and a t-test. And that's when we'll be done after that. Okay, so what's the time right now? I didn't bring my, just want to make sure I have time for everything. Oh, here, I got my phone, never mind. I got it. Okay, we're good. All right, so now significance test for the slope. So why do you do it? Why don't you just do a confidence interval? Well, sometimes people, they want to get a p-value for the null hypothesis, okay? That's very common. So sometimes instead of finding confidence intervals, we just want to get a p-value for the null hypothesis that the true population slope is 0, okay? So the idea is, okay, you ask, if the true we're doing the same thing we always do. We assume the null. If it was truly 0, how likely would it be, just by the luck of the draw, to get a sample slope as negative as what we got, as different from 0 as the sample we found? This is our usual thing. So we do it because people want to get a p-value, because they have a particular hypothesis they want to test. Often that there's no relationship. The p-value, the slope is really 0. Okay, in the population, we just happen to see one in our sample that's non-zero. So basically, what are we going to do? So we're going to be testing, all right, let's just remember. So we'll be testing H naught, that beta, we have a model here. Their model is, in the population, it's these Greek letters, the beta 1 for the slope is equal to 0. And then we have these alternative hypotheses that can either be two-sided or one-sided. For two-sided, it would be beta 1 is not equal to 0. For the one that we with the relationship between drinking and GPA, would probably be one-sided. The beta 1's less than 0 for the one-sided. Okay, so now what would be our test statistic? Well, this looks complicated. It's not. It's just, okay, so let's state what we always do. We'd say, okay, T, let's say we do a T or a Z. We can do a T. So we'd say, okay, we get a sample slope, right? That's what we can see, the observed minus the expected, or observed sample slope, which would be B, instead of beta. Observed slope minus our expected slope under the null, right, over the standard error for our sample slope, but we do a plus. Now this would drop out. Why? Because under the null, it's 0, so we can just cross that out. So that would be our statistic. So what happens here? Well, I just simplified it, that's all. And you can see, so what I did, sometimes I don't know if you want me to write it out again, but you can just see that sometimes maybe it helps. Okay, our observed slope. What is our slope? R times S dy over S dx, right? That's what's in the numerator. Then, and this is from our sample, then what's in the denominator? Okay, that's the standard deviation of errors over the square. It's this right here. It's the standard deviation of the errors, which is the square root of 1 minus r squared times S dy over, and then we'd have to say the square root of n minus 2, and then we'd have to do the S dx. Now, look what happens. This t is in terms of, and z are in terms of pure units. So these cancel out, right? And our test statistic in terms of t and z is going to look like this. It's kind of nice. When we simplify it, we have this over, multiply top and bottom by the reciprocal, and we get r over the square root of 1 minus r squared times the square root of n minus 2. So that's what it looks like. All right? And that's the t statistic with n minus 2 degrees of freedom. It's going to look like this. For big N, we're going to use the z, and everything's the same. We do the same exact thing, except what do you think? It's going to end up, I have it right here, but the z I'm just going to write it in big letters, r over the square root of 1 minus r squared. That's a measure of the strength of our model. This is the measure of the strength of our errors, right? 1 minus r squared is the strength of our errors, fraction of the variance in the errors, and this r squared is the fraction in the model. All right, so it's that, and then just times the square root of n. We're really dividing by n, but yeah, it comes in, which is nice because it says that the bigger our sample size, it's in the numerator, in the simplification, the bigger our sample size, the bigger z will be. So if we have some evidence against the null for a real effect, for a real correlation, then the bigger our sample size, the farther our z and t will be away from 0. More evidence to reject that r is 0. Okay, so that's the idea. So those are going to be our two statistics, t and z. And then we're going to get a p-value. Just the usual. Right? And if we're doing a 95% confidence interval again, right, that would mean we'd have 2.5 and 2.5. And a 95% confidence interval, rejecting the null, is the same thing as not including 0 in our confidence interval. So rejecting H naught at 5%, rejecting H naught if for when the alternative is two-sided, for two-sided alternative, this thing, if we reject it, we land out here. And that's the same thing as not including 0 in our confidence interval. Is the same thing as the 95% Our null is at 0, right? So when we reject the null, that means we landed out here, and it means 0 is not in our confidence interval. Same thing. All right. So that's the idea. And this is the key point. Our test statistic ends up involving only R and N. That's very cool. Only R and N. And we don't have to even deal with those SDs and SYs. This is all we need. So if I give you R and N, you can do these hypothesis tests. You don't need to know the standard. You don't need to go through all this. That's all you need is R and N. See? Okay. So we can do the example, and that will be after we finish this example. Oh, we have to do it a Z and then a T. Is that what we're doing? I was hoping we'd just have one more page. We have 2 more pages. Okay. Oh, no, we're just going to do it as a, this page is almost nothing. We are almost done. I don't know why I'm so eager to be done. It's because it seems so repetitive to me, even though it's supposed to be super hard stuff doing this, and it's not usually covered in an intro stats class. Once we get the concepts down, it gets easier and easier in some ways because they're the same concepts over and over again. All right, so let's say we want to do a test because we're interested in finding out whether or not there's a negative slope in the regression equation for predicting, this is a typo, I'm sorry, for predicting GPA, so GPA is Y, from drinking. That seems more logical. So that is Y, GPA. Whatever you're predicting is, let me remind you, Y is always the variable that you're trying to predict. It's the dependent variable. It's dependent on the drinking. Y is always the variable you're predicting. Okay. So we've done that. And we've already found the slope. Just to refresh your memory, let's just get the equation again. We already found the slope. Oh, gosh. So our slope was what? R times SDY over SDX. This is exactly what we did before. Negative 0.2 times 0.5 over 5. This is from the previous page, and this was what we found. So let's stick it in there. We already have that. Okay, so we take a random sample of 25 students and find this slope. This is how much, small effect, but we want to know whether it's significant. 200th of a point. Some of you care about that on your GPA. Among the 25 students, is that strong enough evidence to conclude a negative slope in the whole population? Here's our sample statistics, and assume our 4 assumptions hold, including normality, because we are going to be doing a t-test. So our sample regression, let's write it in the way I told you to write it, the usual way. You're going to put this first, right? You should be putting, like, this is beta naught, and then you're going to have beta 1 times x1, which in this case is drinks. So it should look like that instead of the usual way. I know you're used to, mx plus b, but in statistics we just go beta 0, b0, b1, b2, etc. Okay, so it looks like this. Y hat, which we're trying to predict, is, and we're going to be adding other things on, so it's a nice way to write it. More variables. Okay, so what do we have so far? We have this, and then we wanted to solve for that. We don't really need it here, but refresher, just to make sure you know how to do this. What do you do? How do you get the intercept? You just put in the point of averages for both of those. So for GPA, we're going to put 3 in, and then we'll just solve for that, minus 0.02 times 10 for drinks. And then we add, that's 0.2, add it, so it's 3.2, solving for that. So that's our equation, and we're focused on the slope. We're not really that interested in that, we're focused on the slope. So So we argue the usual thing. Here's our null hypothesis. What if there really was no slope in the population? So we assume the null. We assume, how likely would it be that we'd get this negative slope? Okay? So the null hypothesis is that our observed difference in the sample slope is only due to chance variation. There's no particular cause for it, so it's just not that unusual. And the alternative, we're going to do the one-sided because we have a reason to believe there's a negative correlation that is too large to be explained by chance, and we think there's a reason for it. We think that the population slope is negative. All right. So now we have to set up this null model. And it's the population scatter plot. And the difference is between the one we did for confidence intervals is we have a null hypothesis in here. We have a scatter plot. Can't be negative, it's just in the positive quadrant. But our null hypothesis is what? That the slope is 0. The slope is 0. That's what it is. This is drinks. This is GPA. And this slope is 0. Beta 1 equals 0. If it was 0, what would our regression equation would be? It would just be, this is the same as, okay, first of all, it's the same as R equals 0. Those are equivalent. It's also the same as what? Our best prediction for Y is the average of Y's, mu for the Y, mu for GPA for Y's is the average of the GPAs. Average in the population, mu. Okay? Average, population average. Okay? Well, of course, because no matter, you tell me how much you drink, we have a completely flat line. The best I can do is give an estimate. To give an estimate would just be the average of all the drinking. So that's the idea. That's what it looks like. That is our null model. And what do? And how many points in here? There's thousands of points, again. One for each UI undergrad. And what are we doing? We're randomly sampling from here. You randomly, that's like randomly drawing from here. You randomly draw n equals 25 points, and it's without replacement. And we get this sample. This is our population scatter plot, and then we get a sample scatter plot. That's what we actually see. And then we get a sample scatter plot that doesn't have a flat line. We get a sample scatter plot that isn't straight. It has a negative line. It's small, but it's negative. Okay, so that's what we get, and it only has 25 points. But anyway, it's like slightly negative. And we have R is equal to negative 0.2, and then we got our slope, we got this, right? We got this equation. This is what we got right here. And beta 1 equal, this is what we're going to be tested, is not 0, it's negative 0.02, that. All right, so all I want you to do is think. What are you going to be thinking? You're going to be thinking of either Z or T. You'll be thinking of, whichever one you're using, your test statistic is going to be like your observed minus your expected, in this case slope, over some standard error, right? that's what you're going to be thinking. And we said for z, it boiled down to what we got on the previous page. Let's just go there. Or t would be equal to the observed slope minus the expected over the standard error plus for the slope. And the cool thing is that these slopes get eliminated and we just get a statistic in terms of, you're going to see we did it before, but just in terms of r and square root of n. It's r over the square root of 1 minus r squared times the square root of n, or for this one, it's going to be r over the square root of 1 minus r squared times the square root of n minus 2. That's what it boils down to, even though it slopes here. All right, so let's do it. Here they are. Okay, so let's do it. So compute z and t. Well, they're given to you right here. Here is z, this is t, and that's z. So let's just do it. So z is going to be r, our sample slope, which is negative 0.2 over the square root of 1 minus r squared, negative 0.2 squared times the square root of 25. Okay? And I did that, and I got negative 1.02. That's z. Now, t is going to be what? The same thing, exactly the same thing, but just multiplied by the square root of 23. So it's just going to be a bit smaller. So it's negative 0.2 over the same exact thing. Now, don't get this confused. This is not t star, which is always bigger. This is just our sample. It's our sample statistic is just a little bit smaller here by a factor, by that factor. Instead of 25 squared 20, we're multiplying by that. And I got negative 0.98. Okay, that's t, not t star. It just has more error in the denominator. Okay, so that's it. And then, so what are we going to do? So now we just have to, so here, let's do a z and a t. So for both of them, we have another axis underneath that's really our sample slope. All right. And we want to match up that with this. All right, so negative 1.02 here, tiny, 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 tiny. And here we get negative, it's almost the same. But remember, this is a t-curve. So this is the normal curve, but this is the t-curve with how many degrees of freedom? 23. Okay? So we need to find that, right? We need to find the t. We need to find this area. Why this area? Why not both sides? We could if you wanted, if we were doing a two-sided. We'd have to do both tails. Okay? Now, all right, t has fatter tails, so we're going to get a bigger p-value here. We're looking at this p-value. And when it's a one-sided test, why is it one tail? Let's just remember, h naught is beta equals 0, and h alternative is beta 1 is less than 0. And that's why we're just looking at the probability that this is going to be our p-value, and you know it's going to be bigger than 5%. But we can look it up. Why don't we look it up on the, if we looked it up here, look what happens. All right, so suppose we wanted to look up negative 0.98 on the t. All right, and we have 23 degrees of freedom here. So here we are. We're just looking at this line. Now, we know positive and negatives, it's symmetrical, so it would be right here, negative 0.98. So all we can tell is what? That it's between, that the tail, which would be the same as this tail, is between 10% and 25%. So we just know that our p-value is between 25% and 10%, but that's a big range, okay? So why don't we use our p-value calculator? Does that make sense, though? Do you understand how I'm reading it off here? Okay, so we might as well use it for both of them, and let's just find out what it is. Okay, so we will go to the document camera and just do that. Okay, so here it is. So the t distribution, 23 degrees of freedom. And we've got a value of negative 0.98, correct? Wasn't that it? Yep. And what do we want? Just the left tail. So it is, we knew it was going to be between 10 and 25, and it's 16.86. Remember that? I'm going to write it down in your book, 16.86. That's the left-hand tail, 16.86%. That's our p-value. And now let's just do the same. Let's do it for the z. And remember, we're going to get a smaller p-value for the z. So let's do that, normal. And we had negative 1.02. We don't have to worry about anything. We want the left tail and compute the p-value, 15.39%. I told you it would be smaller because t has fatter tails. So 15.39, put that in for the, and we're not going to reject the null. Let's go back to our, and we're going to be almost done, right? Let's see. All right, so there it is. So let me think. So this is the degrees. Let's see. So what's our conclusion? We cannot reject the null. Because our p, in both cases, is greater than 5%. So our data is consistent with the null that the population slope, with the population slope equaling 0. So we don't have, even though we found that negative slope in our population, in our sample, we don't have enough evidence with only 25 to conclude it would be like that in the whole population. But with our sample data, we certainly, I think we have enough evidence that at least for stat 200 students, we have a much bigger sample. So we could do it if it was randomly drawn from all potential stat 200 students. We might be able to reject the null and conclude there's a negative relationship in the population. All right, so, and then, by the way, what if I asked you, you know, the 95% confidence interval we already saw does include 0. So, was that for the same exact problem? Yeah. Yep. So it's consistent with that. And consistent with, now this is a one-sided. So it would be consistent with, because it's one-sided, that would be 5% in one tail, 5% in the other, so it would be consistent with the 90% confidence interval, not including 0. Well, if our 95 didn't include 0, our 90th percent, it's not going to. 90th percent, not including 0. I'll just draw the picture for the one-tailed. See, confidence intervals are always in the middle. And when we did one tail, we had to have 5% to reject, right? So that's 90% in the middle. So if it landed at 5% here, way out here, we would have rejected the null, but it didn't. It's less than 5, right? P is greater than 5%. So that would be equivalent to the 90%. Does that make sense, everybody? All right. Because, I should put that down, because H alternative is beta 1 is less than 0. So we're putting all that 5% in one tail. Okay. Sounds good. And let's see if we're finished. We are. And next time we're going to start something really cool called analysis of variance that we're going to be using for multiple regression. We're just going to start it with simple regression. We're going to be using it to test linear models in general. So it's going to be good. That's what we'll do next time. Yes? How do you know if it's a left-hand tail test or right? If it's less, if we're looking for beta less than 0, that means to the left of 0. So it's left. We're looking for extreme values way out here. Okay, we know the direction. In this case, we didn't think that the more you drink, the better your GPA would be, although maybe a lot of people wish that were true. If we thought, oh, you drink, it's going to affect your GPA. It's going to either make it lower or higher, but we're not sure which, because drinking does have a psychological effect, but we think it could have either positive or negative. If that was what we were thinking ahead of time and was our hypothesis, we'd do two-sided. But since we have a lot of evidence that it really damages people's GPA and damages that we think it's going to be negative. That's why. Good question. All right, and that's it. So have a great weekend. And if you haven't picked up your exam yet, we're there 2 to 5 every day until spring break, so come pick it up.